Right, so hi everyone. Thank you all for coming to this talk about causal inference, what it is and how to do it in Python using Causallib. I know it's after lunch, but I hope to keep you sufficiently engaged. So my name is Ehud, as Dean said. Can you get it? So my name is Ehud. I've been a research staff member at IBM Research for the past 8 years or so, working in the machine learning for healthcare group there. So I will mostly introduce you to the concept of causal inference at a very high level. To the concept of causal inference on a very high level, and then show you around a quick tour of Causallib and how to do causal inference in Python. But before that, my brothers recently moved to the UK, and there, when you go to your doctor for a routine check, they often want to assess your risk for a heart attack or a stroke. So you go to the physician. She will fire up her browser, which will go to this very real online risk calculator to assess your risk for heart attack or a stroke. And she will type in your information. You can see it here, your demographics, your clinical information. The list is slightly longer. In this example, we have a hypothetical 55-year-old white male with some family history of heart attacks. And she will she will click calculate risk, and this is the screen you will get. So you can see this person's predicted risk for a stroke within the next 10 years is 11%. Now, I don't know how you approach risk, but this is quite high. If I were this hypothetical person, I would try to figure out what can I do in order to reduce it. And indeed, we see that one of the options is blood pressure treatment, which we know from the medical literature reduces the risk for stroke. So I wonder, what will it do to me, right? How will it change my risk? So take a moment, make a prediction. 3, 2, 1. The risk has increased, which is strange. So this example demonstrates two important limitations of prediction as we know it. The first one is prediction is not enough. Once we are faced with some risk assessment, our mind immediately seeks how to mitigate it. Like, do I need to change my diet? Do I start with sport? What will be my risk if I start a new medical therapy? And so on. And the other part is that we are interested in proper modeling of causal effects, right? Because initiating proven treatment shouldn't increase my risk. Predictions should agree with reality. And to the credit of the authors of this risk calculator, they did not intend to estimate the causal effect of blood pressure treatment, but nevertheless, physicians and patients misinterpret that because this is what they care about. We are causal thinkers. We understand the world through causal effect, and this is what interests us. And so we often would like to isolate the causal effects of the actions that we can take, and this is where causal inference comes in. So causal inference is about quantifying the causal effect of a pre-specified action that is of interest on an outcome, on a pre-specified outcome that we care about. And conceptually, to do that, we will need to compare what would have happened if we did something to what would have happened if we did nothing. And ideally, to make this comparison, we will use the multiverse, because just before an action is taken, the universe splits. In one universe, we did the action. In another, we did not do the action. The rest is identical. And so any downstream effect or difference is only due to this action because everything else is held constant. And so we can isolate the causal impact of just making this action. But unfortunately, in reality, we have no access to the multiverse, right? People either act or they don't. And so that could be like a poor substitute to this hypothetical measure of what would have happened had everyone acted or not acted. And the problem is there could be some preference for who decides to act and who doesn't. So say we are tasked in finding whether blood pressure treatment reduces the risk for a stroke, and we are data scientists, we're very hands-on, we fire up the clinical database, we query for patients who got the medication, we query for patients who did not get the medication, and then we compare the rate of stroke between the two groups. And maybe indeed we see that those who got the medication have higher risk. But that doesn't feel quite right, and we are smart data scientists, so we dig deeper, and we find that age predicts this risk pretty well, and that also that older people tend to get the medication. And so we thought we saw that the medication increased the risk, but we have this age lurking in the shadows in which older people tend to be prescribed more to the drug, and older people having higher risk for a stroke, and so it appears to increase the risk if we ignore the age of those who take the medication. And this is like the source of the famous adage, right? Correlation does not imply causation, except when it does, right? Because this is how we know truths about the world. We knock a glass off the table, it breaks, cause and effect. And what we need to do in this case is we need to disentangle the effects of, say, age and medication. We want to eliminate the effect of those other features in order to isolate the effect of the actions that we take. And one way to do that, which you're probably familiar with, is with randomized experiments, right? Like A/B testing or randomized controlled trials, which are considered like the gold standard for causal effect, in which we randomly assign people to treatment and placebo, right? So now age can no longer influence who takes the drugs because we do that, and we do it randomly. So the age distribution should be pretty similar between those two groups, and when we compare them, they will cancel out, leaving us with only the effect of the drug that we're interested in. The problem with experiments is that they are not always feasible, right? They cost money, they take time, they can be unethical, right? You can't force people to smoke cigarettes and follow them up for years only to prove that smoking causes cancer. But what we do have is observational data, right? This is data that we already collect collect regularly and is quite abundant, right, in this era of data that we live in. But in this type of data, we no longer intervene on the world, so like people self-assign. This is the case that we showed before. People decide whether they act or whether they don't. And so we'll need to use expertise and statistics and machine learning in order to disentangle these effects and isolate the effect of the action. So in causal inference, we will utilize statistics and machine learning, but differently. And how is it different is we can compare. So in supervised learning, we have the features and we have the target, right? Those kind of this type of data. And our task is mostly interpolation. We want to predict the outcome for unseen X, right? For new samples in the test set that we haven't seen before. In causal inference, we have features and we have the target, but we also have this third variable, the action that we're interested in. And now the task is some sort of extrapolation. We want to predict the outcome for unseen A, right? What would have happened if we acted differently? And so we have the prediction that we make is no longer a single prediction. We want to predict under both scenarios, the scenarios in which we didn't take the treatment, and we want to predict under the scenario in which we did take the treatment, we did do the action. But the problem is that we have like inherent missingness in here, because for those who are untreated, we basically know what their outcome is, because we know the outcome had they not been treated, because this is what we observe, this is what they do. But we cannot tell what was their outcome had they been untreated, because this didn't happen, we can't measure it. And so we want to predict outcomes from alternate realities, but we can only observe one outcome based on the action that was actually taken. And so this raises a problem because we have no ground truth labels like we have in supervised learning. So how can we still estimate causal effects if we can't learn them directly? The basic principle will be to borrow information across groups. And so we can use the outcome for those untreated in order to guess what would have been the outcome for those who were treated had they not been treated. And vice versa, we can take the outcomes for those who have been treated and use them in order to make a guess what would have been the outcome for those who were untreated had they been treated. And to do that, we will use two families of methods. One will model the treatment given the features, and one will try to model the outcome directly using the features and the treatment. And there are also composite models that combine both. So quick overview of those of both methods. In treatment models, what we will try to do is to assign sample weights so that we make the feature distribution between groups slightly more similar, right? So we will apply some sort of a function to make the groups indistinguishable. So the only difference between the groups will be whether they were treated or not. Everything else will be held constant. And the action will look random as we would wish in a randomized control trial, in a randomized experiment. And the simplest example, the most common one, is inverse probability weighting or inverse propensity weighting, both abbreviated to IPW, in which we will use some classifier to predict the probability of being treatment, and then we will assign the sample weight we'll assign would simply be the inverse of that probability. And we can demonstrate that, like say we have those groups of treated and control, and if we were to try compare them as they were right now, we couldn't distinguish whether the difference we see is because those are treated or because we have slightly more weird little guys in the treatment group. And so we have 5 in total, 4 of whom are in the treatment group, 1 of whom is in the control group. We calculate those probabilities, we take the inverse, this is our weight, and we reweigh the sample, right? So now, this little guy got replicated 5 times, and they were as well. So now we end up with 5 weird little guys in each group. So the groups are now indistinguishable in terms of being this weird little guy. And so if we now were to compare those groups, the effect of being a weird little guy will cancel out, and we will only be left with the effect of being treated or untreated. We can no longer predict the action, the assignment based on those characteristics. And of course, this is a simple example with a single feature, but if we will have a lot of them, we will use any machine learning probabilistic classifier in order to calculate those probabilities. This is how we apply machine learning, but differently. And in terms of outcome models, so again, we want to predict those outcomes directly given the features in the treatment. And one way to borrow information across groups will be to first to split the data set, right? We fit one model for those untreated and one model for those who were treated. Right, those say the model for the treatment capture the correlation between the features and the outcome among those who are treated. And now when we want to make a guess, we simply cross the prediction, right? We pass those untreated through the model that was trained on the treatment group, and now we can guess and predict what would have been their outcome had they been treated. And this is to say that we can also do it in a single model. We don't need 2 models to do that, which begs the question, what makes it causal, and how it differs from supervised learning. And the answer is that I'm sweeping a lot. under the rug. But there's like a specific choice of the features that we use that will provide like a valid estimate. It's like before, we will need like to know that age is an influencer and adjust for it and make it in the model. So a quick recap before we continue, right? Causal inference quantifies the impact of actions by making those what-if predictions. But the problem is that like we have inherently missing data. We don't have access to those counterfactual outcomes, and we overcome it by estimating or borrowing information across group to reduce bias, and we can do that by modeling the treatment, by modeling the outcome, or modeling both. Great. And so this was how we estimate causal effects in principle. And now, which brings us to how to Causallib and how to estimate causal effects in practice. And so this will be like a brief tour to the package. So Causallib is an open source Python package I created with the help of the team at IBM Research about 5 or 6 years ago. It is scikit-learn inspired both in its goal to be like a one-stop shop for everything causal inference, right? Have the ability to do like both prediction or estimation and evaluation and variable selection and model selection, have toy data, etc. And both in having an API and design that will feel very familiar for those machine learning practitioners who come from the scikit-learn Python ecosystem, scientific ecosystem. It's domain agnostic, so although I gave you examples from healthcare because this is what I'm familiar with, we can translate it to finance or marketing or whatever domain you're working in. And it's easy as being, and getting it is easy as doing pip install Causallib. You can try it as we speak. So a quick tour of the package. We always start with the data. So here as well, we respect this like 3-tuple kind of structure. As we said before, we have the features, we have the action, and we have the outcome. Those are 3 different variables. And once we have the data, we can load the causal model. Now, Causallib implements many models. We have treatment models, we have outcome models, and we have those composite models that I mentioned that combines like both treatment and outcome models. And if you want to go beyond regression and classification, there are also time-to-event models for doing survival analysis, etc. And the way Causallib works, again, it utilizes machine learning estimators internally, right? As we said, we will use machine learning, but we will do it differently. We still need some engine underlying the model that we have to take high-dimensional data and compress it to predictions or to probability, right? So like in this example, we have IPW, and we plug into it a logistic regression models. The logistic regression models will take the data and provide the probabilities, in which we'll do the inverse probability weighting afterwards. And the design of the causal models themselves are interchangeable, and their design is like highly inspired from scikit-learn. They have like a fit predict like API. The only difference is that predict is not very well defined. So we will work, say, with the potential outcomes that we have. That we want to predict the outcomes under different scenarios, right? So, so we first fit the model with the data that we have, and then we make the prediction. Here, I'll show you that. And then we make the prediction. What will be the outcome had everyone been treated? What will be the average outcome had no one been treated? And then once we have those potential outcomes, any contrast between them is what we usually call an effect, a causal effect. So we can take the difference, or we can take the ratio, or whatever. In outcome models, we can also make individual, where we predict the outcome directly, we can also make individual level predictions. And so potential outcomes will look something more similar to that. We will have a value for each of the the observation that we have in our data. We will have the prediction, the individual level prediction, had they not been treated or had they been treated. And again, we can take like any contrast between those two measures and even take like any arbitrary aggregation on top of it. And where Causallib really shines is in its ability to do flexible modeling, to leverage arbitrarily complex machine learning estimators and like mix and match between causal models and machine learning estimators. So just a quick tour. This is like the simplest example that you can apply in order to predict an effect or potential outcomes. Again, we take the IPW model and we plug it in with logistic regression. We fit and we predict. But say we have high-dimensional data and we want to apply some penalty, so it can be as simply as just replacing the logistic regression with some penalized logistic regression and what penalty to use. I don't know. Let's cross-validate to find out. But say we want to introduce nonlinearities now, so we can sweep the logistic regression with some additive trees model, and so, but everything else still remains pretty much exactly the same. And additive trees, now they have their own hyperparameters, so which one to choose, I don't know. Let's do a hyperparameter check, test, and choose the one that is most predictive. Hyperparameter search, I'm sorry, and choose the one that is most predictive. But we can recall that causal inference is not exactly a predictive task, so why select models for predictiveness? We can maybe optimize scores that are slightly more related to the causal inference task that we have at hand, and now we can also do a search over the internal machine learning estimator, but also on the hyperparameters for the causal model, for the causal models themselves, which also have hyperparameters on their own. And the causal models themselves are interchangeable, so we can replace that IPW that we had before with some outcome model to get like individual level predictions. And of course, we have several of those, so we can create like arbitrarily complex models there. And we can even go further as like creating those monstrous ensemble models that like model both the outcome and the treatment, and plug those into those composite models that I mentioned before. And it's not for nothing, because if you can see, we can gain statistical efficiency by doing that. We can extract more information out of the data using complex models, and now we gain precision. The confidence intervals that we have around those predicted effects will be narrower. But since we allow for out-of-sample inference, we also want to avoid double dipping, so we can do the same as we do in traditional prediction. We can split the data set, we can fit on one set and then make the prediction on another. And we can also enable some sort of an evaluation scheme to check both numerically and graphically to compare between models and like get a fuller picture of the model performance. So to summarize, Causallib is an open source package. It's highly inspired by scikit-learn. It should have like familiar design or feel for those who are used to scikit-learn. It also should be easy to use. This is what I heard, but like I encourage you to test it yourself and let me know. I'll be happy to hear. It's a one-stop shop for everything causal inference. It's very industry-oriented in mind that like it's light on dependency. I bet it doesn't add like any other dependencies to your virtual environment. Always use virtual environments. It's well tested or reasonably well tested. It allows composable and flexible modeling of causal effect. There are many examples and case studies at the GitHub repository, and that's about it. So to summarize completely, the most important takeaway here is that prediction might not be enough because we often care about causal effects. And this is true for linear regression as well as it is true for large language models, and you can come fight me afterwards if you don't agree with me. Causal inference allows us to make those what-if predictions and answer the questions that really interest us more directly. So, no, it is possible, even though, again, I swept under the rug probably many details in those 30 minutes. And we can do that. We can make those what-if predictions in an unbiased way if we adjust for other variables, and Causallib can do this adjustment for us flexibly and easily, and we can combine machine learning and causal inference to gain better efficiency from our data. It's available on GitHub. It's available on PyPI. Just pip install Causallib, and thank you very much for anticipating.